This lecture can be treated as a mathematical supplement to our discussion on the WKB method. While studying the WKB method, we saw that this method gave us perfectly good controlled approximations for the wave function in the classically allowed region and in the classically forbidden regions. However, these approximations broke down near the classical turning points, which is why we needed to take special care in deriving connection formulas which will help us to connect the forbidden region solutions to the allowed region solutions and vice versa. While deriving these connections, we actually used the behavior of the Airy functions. In particular, we use the behavior of the Airy functions at large positive or negative values of the argument. In this lecture, what we will do is we will try to ultimately understand this asymptotic behavior of Airy functions. We will first represent the Airy functions by complex integrals and then use what is called the saddle point method to try to understand the asymptotic behavior. Let us begin now with a cousin of the saddle point method. This is the method of steepest descent, also known as Laplace's method. By the way, this method is often also called the saddle point method, despite the fact that the name saddle point method should really be reserved for the case of complex contour integrals. Come to think about it, even the name steepest descent is derived from the way this method works in the case of complex contour integrals. However, it is quite common to call this method the method of steepest descent, even when we are referring, as right now, only to real integrals. The reason why we are starting here is both that this is a simpler version of the saddle point method and also that this in itself is a very important method which is useful in many different places. So setting of this method is as follows. We want to consider an integral capital I of A from some point x1 to some other point x2 on the real line of the function f of x times e to the power capital A g of x. And what we are looking at is g of x has a maximum at x equal to x0, where x0 belongs to the interval x1, x2. So it is somewhere inside the interval. We also demand that the value of the function f does not vanish at x0. We want to explore the behavior of capital I of A for very large positive values of A. And indeed, what we are going to do ultimately is derive an approximate result for I of A, which gets better and better as A becomes larger. Let us start with some basic consideration about the integrand that we are trying to integrate. Note that g of x has a maximum at x0, which is somewhere inside the interval of our integration. This has been multiplied by a large number, so the maximum really will be very large, and then it has been exponentiated. This immediately shows that this integrand f of x e to the power a times g of x will have a rather sharp maximum at x equal to x0. The width of the maximum will actually be controlled by the parameter a. Just to see that, note that ag of x can be approximately written as ag of x0 plus g double prime x0 by 2 factorial a times delta x whole square. All we have done is we have used the Taylor expansion of g of x, where delta x of course is x minus x0. And what we have used is the fact that the first derivative of g vanishes at x0, and we have truncated the series or approximated it by retaining up to the quadratic term. So the exponential of agx, the dominant factor in our integrand, is going to be approximately e to the power a g x0 times e to the minus g double prime x0 magnitude by 2. Note that g double prime x0 has to be negative because g is a maximum at x0. So e to the power minus g double prime x0 by 2 times a delta x whole square. So notice that the quantity a delta x whole square controls the behavior of the peak. This is like a nice Gaussian curve, and the bigger a is, the narrower the curve is going to be. And it is very easy to see from this expression that the width will sort of fall off as 1 by root a. So if you make a 4 times bigger, the width will become halved. That is simply because when a is 4 times bigger, you need a delta x which is only half as big as before to provide the same negative exponent and hence bring down the curve by the same amount from its peak. Since most of the contribution to the integral will come from a region of the width 1 by root a around x0, what we do is we change variables to reflect this fact. We go from x to the variable y, where the two are related by x equals x0 plus y by root a. The 1 by root a prefactor has been put along with y simply to ensure that in the region where you are going to get substantial contribution from, y is of the order of 1. With this expression for delta x, which is y by root a, we can expand out pieces of the integrand a times g of x and f of x in Taylor series. This Taylor series is going to look a bit intimidating at this stage, but note that if you were interested only in the lowest order or leading order terms, the actual calculation would be a lot easier than it seems by looking at these expressions. I've decided to keep higher order terms also in this expression because we want to figure out how good our approximation is going to be. So in the real life applications, it is not enough just to have an approximation to a particular result. It is very important also to have an idea about how good or bad this approximation is. That is why we are actually going to calculate beyond the leading term here. A times g of x is obviously a times g of x0 plus g double prime x0 by 2 factorial into y by root a whole square, that's y square by a. Then you have g triple prime x0 by 3 factorial y cube by a to the 3 by 2 plus 4th derivative at x0 by 4 factorial y to the 4 by a square and so on. Note that because of the a outside, what you end up with is that the quadratic term in y actually is independent of a here. You have ag x0 plus g double prime x0 by 2 factorial y square plus higher order terms which have 1 by root a, 1 by a and so on. We can easily expand f of x out in the Taylor series. This is absolutely trivial, and f of x of course does not have a maximum or a minimum necessarily at x equal to x0. So the first derivative may or may not vanish. Assuming that f of x0 is not 0, you can always write that as f of x0 into 1 plus f prime x0 by f of x0 into y by root a plus f double prime by 2 factorial f of x0 in the denominator into y square by a plus higher order terms. Note that what I have really done is keep up to order 1 by a in both ag of x and f of x. Now that we have all the pieces, let us put them together. Of course, the major contribution to the integral will come from the exponential e to the agx. And so what we do is first write e to the agx by noticing that agx0 gives you a factor e to the agx0, which is a huge contribution because a is very large, remember. However, this particular contribution is a constant, so it will be easy to take care of that in our integral. The next term is independent of a, and that is going to be a first order correction beyond the dominant term which we will get from the constant piece. The rest are suppressed by negative powers of a, and because we are going to ultimately work with very large values of a, what we can always do is treat the rest of the exponential as the exponential of a small quantity and expand it out using the exponential series. So exponential of this term with e to the minus half and this term with e to the minus 1 and the rest essentially can be written down as a sum of this term plus this term squared and so on. Let me assure you at this stage that the reason why we are keeping these further terms which are suppressed is basically because we want to make sure how good our approximation is going to be. Because those terms are going to give us correction terms beyond the leading ones. Now, let's just form our integrand by multiplying f of x by e to the agx. That of course gives us fx0 e to the power agx0. This piece is a constant, so it can be taken out of the integral. Next comes the part which depends on the variable y. The first piece, e to the g double prime x0 y square by 2, as I have said, is independent of capital A. And this is going to give us a dominant term from the integral itself. Please note that g double prime x0 is negative. So this is essentially of the form of a Gaussian. And that is what we are going to exploit in order to calculate the integral later. I have emphasized that here in the next stage by showing explicitly that minus g double prime x0 comes with an overall minus sign here. This quantity minus g double prime x0 of course is positive. But before we go there, what about the correction terms? You get this correction term or this bunch of correction terms from e to the power agx. Let me just point out that what I have done here is collected the powers of a, or rather negative powers of square root of a here. So the first term here is the only term which you get from this expansion, which has e to the minus half. E to the minus 1 actually comes from two terms, this one as well as the square of this one, and putting them together you get this slightly formidable looking term, which is the only contribution you have to this correction factor to the order A inverse. Of course there are higher order terms, but we are not going to bother writing them down. Now you can collect all of these together and essentially write this integrand as f of x0 e to the agx0, once again the term which is independent of the variable y, plus a term independent of a, which is going to dominate the integral. And then what we have are terms which are going to be very small for large A, but which we have retained here simply to show you how good or how bad this approximation is going to be. I grant you that this calculation looks a bit intimidating, but all we have really done is collect the terms together and use very simple algebraic manipulations to arrive at this. Let me also point out that these rather formidable looking things in the brackets here are all polynomials in y. And because you have an overall Gaussian exponent outside, the integration really is rather easy to do. So what we are going to do now is estimate our integral, which of course is the integral from x1 to x2 of fx into the agx. We have just plugged in our expansion or approximate version for fx gx e to the agx here. So what we have is fx0 to the agx0 times the Gaussian term, and then we have these correction terms put together. Of course, because you are changing the variable from x to y, dx becomes dy by square root of a. And so what we can do is put them all together in this form. fx0 to the agx0, as I have been saying, moves out of the integral trivially, being a constant. You have this 1 by root a from the measure moving outside as well. And we change our limits from x1 to x2 to y1 to y2. Notice that as long as a is very large, the contribution only comes from the immediate vicinity of the peak. And if the peak is somewhere in the interval, not at the very edges, then for large enough a, the Gaussian is going to make the whole thing die down rapidly before it gets even close to the edges. As a result, it is perfectly legitimate to approximate this expression by replacing the limits y1 and y2 by minus infinity and plus infinity respectively. All we are saying is that for the infinity long stretches we have added to the integration interval, there the integrand is too small to contribute anything meaningful. So what we have is an integral from minus infinity to plus infinity of e to the power minus mod of j double prime x0 times y square by 2, a perfectly nice Gaussian integrand, plus correction terms which are in negative powers of square root of a, and each of the terms in these integrands, no matter how complicated they look like, are essentially polynomials. So what we have in these integrals ultimately are very simple things. There are some polynomials multiplied by a Gaussian factor, and you can calculate the integral using elementary methods that we have already learned for evaluating Gaussian integrals. And these methods tell us that the integral is going to be, apart from the constant factor, simply square root of 2 pi by minus g double prime x0, the familiar Gaussian integral, plus further terms which essentially comes from integration of the polynomials. Now, one thing you may have already noticed, that the polynomial which multiplied into the minus half is an odd polynomial in y, and so its integral, when done from minus infinity to plus infinity, will definitely vanish. And this works not only for e to the minus half, it also works for e to the minus 3 by 2, e to the minus 5 by 2, and so on. All further terms down the line, all these are multiplied by odd polynomials in the integrand, and hence they vanish in the integral. So first leading order correction beyond the root over 2 pi by minus g double prime x0 which comes from the Gaussian is suppressed by a factor of 1 by a. It's 1 by a times a constant c2 which comes from calculating the integral. Now you can easily calculate the integral using our familiar Gaussian integral results which are listed in the box on the left here. All you need to do is use the integrals that I have listed in the box here to evaluate the integrals of y square times e to the minus g double prime x0 y square by 2 and so on. And once you calculate these integrals, it's a pretty straightforward though slightly tedious thing to do. You're going to end up with this particular expression for the constant c2. You can of course come up with expressions for the constant c4, c6 and so on, but they are going to be even more cumbersome, and they are suppressed anyway by large negative powers of a. So for large a, even the first correction due to c2 by a is pretty small, but that is going to give us an idea of how good our estimate, which is the rest of the thing, is going to be. So there you have it, our steepest descent approximation for the integral f of x e to the agx dx from x1 to x2, provided that there is a maximum x0 of g of x somewhere in the interval. And this approximation is going to be given by f of x0 e to the agx0 times square root of 2 pi by minus ag double prime x0 multiplied by a correction factor. This correction factor has 1, of course, as its leading term, and further terms are suppressed by negative powers of a, c2 by a, c4 by a square and so on. So for large enough a, you can even ignore all these terms and stick to this particular approximation for the integral f of x0 e to the power agx0 by square root of 2 pi by minus ag double prime x0. Now there are a few points which has to be borne in mind here. If there are multiple maxima in this interval from x1 to x2, then the largest one, the global maximum, dominates. If more than one maximum of gx has the same value, their contributions have to be added together. Let me now illustrate all that we have talked about above by taking a look at a few examples. The first example we will look at is this integral. The integral of x e to the power 100 sin x dx from 0 to pi. Here, the function f of x, the prefactor is obviously x. G of x, the function in the exponent, is sin of x. And the role of a is being played by this number 100. And in order to evaluate the integral, what we need are these simple details about the function. Sin x, of course, has a maximum in the interval 0 to pi. And as you all know, the maximum happens to be at pi by 2. So this is our x0. And the value of f of x0 is simply pi by 2. G of x0, sine of pi by 2 is obviously 1. And g double prime x0, pretty straightforward calculation which everybody knows the result of, is minus 1. In order to calculate C2, the correction, we also need the values of f prime at x0, f double prime at x0, g triple prime at x0, and g fourth derivative at x0. All of these are pretty easy to evaluate, and by plugging these values into the formula, you get C2 equal to 1 by 8. Once again, if you are only interested in the leading result, you don't even need to evaluate C2 because you know that its contribution is suppressed by a factor of A. But here we can take a look at whether including the C2 by A term actually improves our approximation or not. So plugging all of these results in, you get the leading order saddle point approximation. Is f of x0 it is the ag x0 times square root of 2 pi by minus ag double prime x0. That's simply pi by 2, it is 100 into square root of 2 pi by 100. And this ultimately gives us pi to the 1.5 to the 100 by square root of 200 as a leading order saddle point approximation to the integral. Let me point out that the integrand here is very sharply peaked around x0 equal to pi by 2. Of course, a larger value of a would have given you an even sharper peak. Of course, sharper but taller peak. As you can perhaps see, although these numbers are too tiny, from the scale here, the peak is of the order of 10 to the 43. So you expect the integral really to be huge. We will now explore how good this approximation is by making use of the quat function from scipy.integrate module. If you want to use any other computational method, you're welcome to do so. This just gives me a quick, fast way of evaluating the integral numerically and also checking out whether the approximation that we have developed, that is square root of pi to the power 3 times e to the power 100 by square root of 200, whether that's actually any good or not. So the value of I, the integral evaluated using the quat function, turns out to be 1.05975 into 10 to the power 43, a huge value of course, and I approximate, our approximation from the saddle point approximation is 1.0584 into 10 to the 43. So you can notice that it is actually correct to 1 part in 1000. To see how good this really is, let us take a look at the ratio I by I app. And that turns out to be 1.00125, followed by some further numbers. Notice that C2 was calculated as 1/8, and C2 by A, 1 by 800, is exactly 0.00125. So, not only is the initial approximation pretty good, because it differs ratio-wise from I only in 1 part in 1000, after you take the first order correction term C2 by A into account, the approximation is rather fantastically good. You have actually got the I by I app ratio correct up to 5 decimal places here. 0.00125, all of them are correct. In fact, if you evaluated C4, 1 plus C2 by A plus C4 by A square would actually be very, very close to this ratio that we have calculated. So, this should convince you that the saddle point approximation is really rather good, at least for large values of A. Now, just to see whether the size of A really matters, let us repeat the calculation this time for the value of A equals 200. And this is the approximate value for A equal to 200. That is, you have replaced the e to the power 100 in the previous calculation by e to the 200, and the square root here, instead of being square root of 200, is now square root of 400. And now the I by I app ratio is actually even better, even closer than the one which you had previously. The previous value was 1.001, this is 1.0006. The error has essentially halved. if you think of the error as the deviation from 1 which you had. And that's easy to understand. Here you have changed your A from 100 to 200, you have doubled the value of A, and the correction term C2 by A actually has fallen. I'm referring to that by the error simply because in most calculations we will not bother to really determine how much C2 is. We are going to just ignore C2 by A, and as a result, the terms that involve C2 by A, C4 by A square are really error terms in the saddle point approximation. And as you can see quite clearly, the error term is really rather small for large values of A and falls off rapidly as A increases, as was to be expected. But let me just point out one thing. Is it correct to say that the approximate value is actually going to approach the actual integral in the limit when A becomes very, very large? The answer really is no. And that may sound paradoxical, but realize one thing. The integral itself is huge and grows exponentially with A. So even if the ratio I by IAP actually gets closer and closer to 1 as A increases, the gap between I and IAP actually increases with larger values of A. Simply because I rises much more rapidly, exponentially rapidly, compared to the suppression of the error, which occurs only as 1 by A. So this is what is called an asymptotic approximation. So here, the approximate value does not approach I as a limit, but the ratio between these two values approaches 1 in the limit of A going to infinity. This distinction is really very, very important. And let me point out that many of the familiar approximations that you have used, especially for large values of parameters, are really approximations of this kind. Asymptotic approximations rather than approximations which become better and better in the limiting sense. Our next example is one which you have actually seen before several times, I guess. And this is an approximation for the value of the gamma function. Gamma at lambda plus 1. I have deliberately chosen gamma of lambda plus 1 to simplify the integral a bit. More importantly, I have chosen gamma of lambda plus 1 because for integer value of lambda, this really is lambda factorial. And what we are looking for here is an estimate for lambda factorial when lambda becomes very, very large. Once again, an asymptotic estimate rather than a limiting estimate. And this is an estimate which you actually know pretty well. This is, of course, what we call the Stirling approximation for the factorial. So what we are trying to do here is use a steepest descent approximation to arrive at Stirling's approximation for the factorial. Now, in order to do this, we must rewrite our integral in this form, which is a form relevant for the steepest descent approximation. A here is a large parameter. Of course, we already have a large parameter in our integral, which is the quantity lambda. But notice that here x to the lambda is sitting outside the exponent. So it is direct. This form is directly not of the form which is amenable for steepest descent. Well, we can of course rewrite it in this simple form where the lambda does go into the exponent. So you have lambda log x minus x. Now this can be recast in this form simply by writing it as e to the minus x times e to the lambda log x, where we might attempt to use log x as g and e to the minus x as f of x. However, this is not going to work for the simple reason that log x, the thing which multiplies lambda, does not have a maximum within the interval of the integration. Log x is a monotonically increasing function and it only peaks at the edge which is at infinity. So we cannot really use our steepest descent approximation directly in this form. But the integrand here lambda log x minus x does have a peak, and the peak is easily seen to be at x equal to lambda. The problem is we need to separate out the large parameter capital A, or here lambda, from the function which we are integrating or using in the integration, this g of x. The fact that the peak of lambda log x minus x is dependent on lambda, of course, shows that you cannot use lambda log x minus x directly as g of x. But this value of the peak immediately suggests a simple substitution which will bring the integral to the form that we want. And this is simply replacing x by a new variable z, which is x by lambda. This of course puts the peak of z at 1, which is independent of lambda, and it's easily seen that now gamma lambda plus 1 becomes lambda, which comes from dx being lambda dz. The limits of course stay 0 to infinity as long as lambda is positive, which it is, at least in this calculation. Then you have e to the lambda log lambda z minus lambda z, and this simply gives you, apart from this e to the lambda log lambda which comes out being a constant, integrand of the form e to the power lambda log z minus z dz. So now we do have our standard form. This quantity log z minus z is going to be our function gz. There is no f of z, which means f of z really is 1 here. So this is our setup. F of z is 1, g of z is log z minus z. So we can easily calculate all the derivatives that you need. The value of g prime z immediately gives you z0, where the location of the peak is z0 equal to 1, but we knew that already. We knew that the original peak was at lambda, and now you have just taken x by lambda as the variable z, so its peak is of course going to be at 1. You need the second derivative g double prime z at z0, and that comes out to be minus 1, as it should be. It has to be negative at the peak. And then you can calculate the further derivatives, g triple prime, g fourth derivative, and so on. And using all these values, you can calculate C2 by substituting all these rather simple numbers into this rather large, formidable looking expression. The final result works out to be very simple. C2 turns out to be just 1 over 12. So let us now take a look at what Stirling's approximation becomes. This is what steepest descent method tells us. Gamma lambda plus 1 is lambda e to the lambda log lambda times e to the power lambda, the value of g at z0, times square root of 2 pi by minus lambda g double prime z0 plus a correction factor. If you put them all together, you get this expression e to the lambda log lambda minus lambda into root over 2 pi lambda by 1 plus 1 by 12 lambda. This is exactly what Stirling's approximation is. In fact, in most calculations, you just use Stirling's approximation in the form n factorial, that is n plus 1 as an argument for gamma, n in place of lambda here. In most cases, you just get away with using this. But this actually tells you that you have further correction of the form root over 2 pi n. Then you know that you have further corrections of the form 1 by 12 n and so on. For most practical applications like the ones you do use in statistical mechanics, n is so huge that this is a term, the constant term, which dominates. So you often even ignore root over 2 pi n, because when you take the log of this, and you need to take the log of this in most calculations, n log n minus n is much bigger than log of root over 2 pi n. So this is the most familiar form for the approximation that you use. N factorial is equal to the n log n minus n. The steepest descent method is not the only way to derive Stirling's approximation, but it is one of the most convenient and straightforward ways of arriving at that result. Let us now move away from the real line and move on to the complex plane. So here we are talking about the saddle point method proper. What we have been doing so far has essentially been a warm-up for this. Now what we do here is superficially very similar to what we have been doing so far. We are looking for the behavior of an integral I of a for a very large positive value of a parameter a, and the integral is of f of z e to the power a gz dz over some contour c. The difference here, of course, is that z is a complex number, and not only that, f and g are complex functions. They are not just any complex functions. We are going to assume that they are analytic functions of the argument z, at least in an open neighborhood containing the contour c. Of course, the other main difference between this one and the cases we have been tackling so far is that here the integral is being done over some contour c, over the complex plane, rather than over a part of the real line. Since we are going to deal with complex functions and analytic functions in particular, let us quickly recall some basic facts about complex analysis. As you all know, any complex quantity can be written down as a sum of a real part and a purely imaginary part. So for example, z, our independent variable, can be written down in terms of two real variables x and y in the form x plus iy. Similarly, any function of z, let us for the sake of definiteness talk about g of z here, can be written down as two functions, one purely imaginary and the other purely real. The real part function u of xy and the imaginary part function I times v of xy together make up our function g of z. It follows from elementary calculus that g prime can be written down in terms of ux plus I times vx, where the suffix x here denotes partial derivative with respect to x. This is the expression for the derivative that you would get if you were to approach a given point purely along the real axis. Well, in a complex plane, you can approach a point along any direction, and the derivative, which is a limit, will exist only if the limit is the same no matter which direction you approach from. You could, of course, also approach along, say, the purely imaginary axis, and if you do that, the derivative works out to be minus iuy plus vy, and since these two must be equal for the derivative to exist, a necessary condition for a function to be differentiable is as follows. Ux must be equal to vy and uy must be equal to minus vx. These are the celebrated Cauchy-Riemann conditions, and I'm pretty sure you're all familiar with them. Given these conditions, we can write the derivative of the function g prime in terms of derivatives of only either the real part or only the purely imaginary part. Can write it either as ux minus iuy or vy plus ivx. They are both, of course, the same now because of the Cauchy-Riemann conditions. Note that we are trying to integrate f of z e to the power a g of z, and in this, for large positive a, the dominant term, of course, will be the exponential e to the a g of z. Now, e to the a g of z can be written down simply in this form, e to the a uxy times e to the I a vxy. The second term gives you a pure phase of magnitude 1. Hence, if you look at the magnitude of this piece of the integrand e to the a g of z, it is given by e to the power a uxy. So basically the magnitude of the integrand is controlled by the real part of this function g. So in analogy to the real case, it would be great if the contour that we had passed to the maximum of u of xy, because we would expect that maximum to sort of dominate the integral. There are some further caveats here and we are going to explain them soon. But if this happens at the point z0 given by x0 plus iy0, you must have both ux and uy vanish there. And because g prime is ux minus iuy, this means that g prime, the derivative of g at the point z0, must be 0. So basically we are looking at a point where the derivative of the function in the exponent, g of z, vanishes. One problem is that this critical point z0 may very well not be on the contour that we are integrating along. However, we have this advantage from complex analysis that the contour C can be deformed without changing the value of the integral as long as you do not pass through any singular point of the integrand. That gives us a lot of leeway. This is the celebrated Cauchy theorem, and this helps us to deform our contour so that it passes through a point where the derivative of g vanishes. So we would like to deform it so that it goes to this maximum of u of xy. Unfortunately, u, which is the real part of a purely analytic function, is something which is called a harmonic function. An immediate consequence of the Cauchy-Riemann conditions is that uxx plus uyy, that is del 2u del x2 plus del 2u del y2, must vanish. And such a function cannot have a local maximum or minimum. simply because the 2 second derivatives of u with respect to x and y respectively have to have opposite signs. So it is impossible for you to either get an absolute maximum or an absolute minimum this way. The condition ux equal to uy equal to 0 will lead not to a maximum or a minimum, but to a saddle point for the function u. This, of course, is what gives the name saddle point to this method. Here I have tried to graphically depict this notion of a saddle point. If you focus on the picture on the left, here what we have done is drawn x and y along the two axes here. These are the real part and imaginary part respectively of the variable z. And we have plotted u along the third axis. So a typical function u, which has a saddle point, would have a graph which looks like this, at least locally. In addition to having a saddle point, which is right here, that is, the saddle point of course is at a point z equal to z0, but the point on the surface which depicts the value of u is sitting on something which looks like the saddle of a horse, which is why, of course, it's named that way. As you can see, it is a minimum of the function if you go along this path. It's a maximum if you go along this direction. Now there's some more detail in this figure which is going to be very important towards the understanding of the saddle point method. And that is something which we have to take a look at carefully. The dotted line here that we have drawn, this blue dotted line, depicts a level curve. So all points on this line have the same value of u as at z0. So basically what you are saying here is that u of x comma y is equal to u of x0 comma y0. This depicts the equation for this dotted line. There are points for which the value of u is bigger than u at x0, y0, the hill. So these are the points which have been marked on the surface in blue. And the points marked in yellow here are the points in the valleys. That is, the points where the value of uxy is less than u of x0, y0. The level curve, of course, is a boundary between these two regions. Let us now turn to the figure on the right. This is actually a projection of the figure of the left onto the xy plane or onto the Argand plane where the variable z is being plotted. So as you can see, at z0, we have the saddle point. The dotted blue line here, as in the figure on the left, stands for the level curves. So these are the values of x and y, where u of xy is equal to u of x0, y0. The only difference between this picture and the one on the left is that in the one on the left, we have depicted these points on the surface u, x, y, u as a function of x and y. Here, we are depicting what is happening in the xy plane itself. The blue dotted region on the xy plane depicts the hill, that is, set of points where u has a higher value than at the saddle point. And the yellow points marked in yellow are, of course, the points which are in the valley, which are points where the value of u of xy is less than u of z0. Now, there are two specific lines, one in the hill and the other in the valley, which are of great interest, especially the latter one. You have a line of steepest ascent and a line of steepest descent. So the line of steepest ascent is a line along which the value of u increases most rapidly as you move away from the saddle point. And the line of steepest descent is one along which it decreases the most rapidly as you move away from the saddle point. In both cases, you're using the saddle point as a sort of reference. So when you say u increases most rapidly along the line marked with red dashes, you mean as you move away from the saddle point in either direction, u increases as fast as it can. And a similar statement can be made about the line drawn with dashed black lines, that is the line of steepest descent. Now let us make a quick point here. if our contour goes through z0, the saddle point, while sticking to the valley throughout, it means that our function u of x comma y reaches a maximum value when it hits z0. So if your parameter a is large enough and thus will cause to a very steep change in the exponent, you can hope to get the largest contribution from the immediate neighborhood of the point z0, which is exactly what we used earlier when we talked about the contribution from the maximum dominating the result for the real integral. A very similar thing can happen here as well. The important thing is your contour has to stick to the valley and not stray onto the hills, because if your contour were to deviate into the hills, then u of xy from those points in the hills could be even larger than the value at the saddle point. However, what is very important is that you must realize that you are not really integrating e to the power a u xy. What you are integrating is e to the power a g of z. And here, in addition to e to the a times u xy, you also have this phase term e to the I times a v of xy. And because a is very huge, you would typically expect e to the I a v xy to rapidly fluctuate in phase. And as should be obvious, a very rapidly fluctuating phase term will actually tend to cancel out the contributions from each other and lead to a highly suppressed contribution from z0. So just merely crossing the saddle point while sticking to the values is not enough. You have to ensure that this fluctuation of the phase is minimized as far as possible. And this brings us to the critical point of the saddle point method. You should cross the saddle point z0 while sticking to the valley along a contour that keeps v of x comma y fixed. As a result, as you move along the contour, the phase will not change, so you are going to get a fixed amount of contribution from that. Of course, this implies that as you move along the contour on the xy plane, vx dx ds plus vy dy ds, which is the rate at which v changes as the parameter along the curve changes, has to vanish. Now, this tells us that our contour cannot move in an arbitrary direction. It has to move in such a way that dx ds and dy ds, the components of tangent to the contour, is actually perpendicular to this vector formed by vx and vy. But using the Cauchy-Riemann conditions, this actually tells you that this path is actually also minus uy dx ds plus ux dy ds equals 0. What that means is this tangent t, dx ds comma dy ds, a vector in 2 dimensions, has to be perpendicular to minus uy comma ux. But that immediately tells you that it's parallel to ux comma uy, which are nothing but the components of the 2-dimensional gradient of the function u. So here, as you move along the direction which maintains a constant value for the phase, a constant value for the purely imaginary part vxy, Cauchy-Riemann condition ensures that in doing that, you are actually moving along a direction where u is going to change the fastest. Remember, the rate at which a function changes is basically the gradient dotted with the displacement. And if your displacement happens to be in the direction of the gradient, you're going to get the most rapid increase or decrease, as the case may be, depending on which way you're moving. So basically what we have ensured here is that by moving along the direction which keeps the phase fixed and hence does not cancel out the contribution which you get from the immediate neighborhood of the saddle point, you are actually moving along a direction which increases or decreases u the most rapidly. And because you are sticking to the valley, what you're going to get is a direction of steepest descent. The corresponding direction in the hills would have been the direction of the steepest ascent. So just to go back a bit, in this figure, the line marked with the black dashes, the line which sticks to the valley, is the line of steepest descent. This is the line on which v of xy is a constant and u changes most rapidly, possible, but it also is the line along which u decreases most rapidly. Along the red dashed line, on the other hand, which is in the hills, the value changes most rapidly as you move away from z0, but it changes by increasing. So that's the line of steepest ascent. This line of steepest descent is going to be very, very important for us. We would want our contour to proceed along the line of steepest descent, or at least proceed along a segment of the line of steepest descent in the neighborhood of z0, so far so that by the time you deviate from that line, the exponential e to the power a uxy has fallen rapidly. Now, since the magnitude of your integrand is very, very small, even if you move away from this line, which maintained a constant phase, and get rapid fluctuations in phase, you don't have to worry about it any longer because the amplitude of the integrand has already died down a lot. So the whole idea here is we will try to deform our contour in such a way that it will go through the saddle point or points, there may be multiple number of them, in such a way that at least in the immediate neighborhood of the saddle point, the curve is going to go along the line of steepest descent. What is very important is when you are far away from the saddle point, you can move away from this line of steepest descent without hurting your prospects much. But what you can never do is stray into the hills, because once you get into the hills, the large exponential amplitude that you get might produce a contribution which will overshadow whatever you're getting from z0. Now, all this talk about hills and valleys is almost making this sound like a geography lesson. And let me confess, geography was never my strong suit in school. Having said that, let me point out that in situations where you have a single saddle point, using the saddle point method is really quite simple. You don't really have to worry about all these issues so much. What is critically important is that you have to deform your contour so that you go through that single saddle point in the direction in which the exponent g of z is decreasing most rapidly. And usually that is pretty easy to figure out just by looking at the function itself. So let me try to illustrate how this method would work in practice. Notice that what we are doing is we are trying to integrate f of z e to the power a gz dz over the contour c, and we can of course deform it to any other contour c prime as long as we don't hit any of the singularities which f of z or g of z might have. And using the expansion around the saddle point, it's pretty easy to see that I can rewrite this integral in the form f of z0 in place of f of z into e to the power a g of z0 plus half g double prime z0 into z minus z0 whole square plus further terms. Now these correction terms are very similar to the ones that we encountered when we were talking about real integrals a while ago. However, we are not going to repeat that particular kind of lengthy calculation all over again. If you are interested in the higher order corrections to the saddle point result, of course you have to take those terms into account. But there is nothing very special about that part as far as complex integrals are concerned. It is almost the same as what you did for the real integrals. So let us now forget about those correction terms and let's focus primarily on the saddle point approximation. Now, the important point is, as was the case for the real integral, for large values of a, only a small segment of the contour near z equal to z0 will contribute. This assuming that we have been able to deform the contour in such a way that not only does it go through the saddle point, it goes through the saddle point in the direction where steepest descent takes place, so that only in a small segment around z equal to z0 do you really get substantial contribution. Far away from that, the contribution nearly vanishes. Now this brings us to the one point that we have to be careful about here. The quantity g double prime z0 in general now is a complex number. It definitely does not have to be a negative real number all the time. So in general, g double prime z0 is going to be mod of g double prime z0, which is of course always positive, times the phase factor e to the I alpha, and alpha can be chosen to be somewhere in the interval from 0 to 2 pi. Of course, you will not take 2 pi if you have already taken 0. Now, our job is to try to find the direction in which the contour has to cross the saddle point in order to produce the steepest descent. And that's pretty easy to figure out, because all you really need is that this term in the exponent, the half g double prime z0 by z minus z0 whole square, causes the exponent to fall as fast as possible. And that will of course happen if this thing is purely negative. Now note that when you are close to the saddle point z0, you can write z as z0 plus tau e to the I phi, but tau and phi are both real. And now the quadratic term, half g double prime z0 by z minus z0 whole square, is easily seen to be half of g double prime z0's magnitude times tau square into e to the I alpha into e to the I 2 phi. The 2 phi coming in because you are squaring z minus z0. Now what you want is that this term should cause the exponential term to drop as fast as possible. That is, this term should be purely negative. Since half mod of g double prime z0 into tau square is definitely real and positive, what we must have is e to the I alpha plus 2 phi must be minus 1. That is, alpha plus 2 phi must be pi, and this tells us what phi must be. Phi must be pi by 2 minus alpha by 2. And once we have that, all we have to do is switch our variable of integration from z to tau, and this becomes a standard Gaussian integral. Of course, the limits here would really be limits which would be dictated by the short part of the contour where you are following this path of steepest descent. However, as we had argued before, since the exponential will come down very, very rapidly, in this case, I had forgotten an a here, that would be the cause for this extremely rapid descent. You can easily change the limits from whatever finite values they have to minus infinity for the lower limit and plus infinity for the upper limit, simply because the exponential, Gaussian exponential, brings the whole thing down so rapidly that the extra piece that we are adding to the region of integration will hardly make a difference. So the only novel thing that you have now is this extra factor which you are getting because of this choice of the direction in which you are going to traverse the saddle point. Note that z minus z0 being tau e to the I phi essentially tells you that when you are moving away from z0 along the contour, you are moving in a particular direction. You are making an angle phi with the real axis. And that is the extra factor that comes in now. The change of measure from z to tau brings in an extra factor of e to the I pi by 2 minus alpha by 2, that is e to the I phi. And so the saddle point approximation for our integral simply becomes f of z0 e to the power a times g of z0, which is just the value of the integrand at the saddle point, times square root of 2 pi by mod of g double prime z0 times an a, and on top of that you have this extra phase factor e to the I pi by 2 minus alpha by 2, or simply e to the I phi, where phi is the angle at which the contour must cross the saddle point in order to ensure that the quadratic term sitting in the exponent is actually negative. Let me round off this lecture with one example. This example is again something which should be familiar to all of you. This is nothing but the binomial coefficient NCM. What we want is an expression that will give me an asymptotic form for this for large values of m and n. And just to simplify the notation, what we are doing is we are using this notation that the m by n ratio, which is of course a number between 0 and 1, is p. Since m and n are both large, p is a number of the order 1, but of course less than 1. Now, NCM, as we all know, is a coefficient of z to the m in the expansion of 1 plus z to the n. Now, if you divide 1 plus z to the n by z to the m plus 1, then NCM becomes the coefficient of 1 by z. And Cauchy's residue theorem tells you that if you were to integrate 1 by z to the n by z to the m plus 1 along any closed contour which contains the singularity, which in this case is at z equal to 0 at the origin, you are going to get 2 pi I times the residue, which is of course nothing but the coefficient of 1 by z. So if you multiply this contour integral by 1 by 2 pi I, the Cauchy residue theorem guarantees you that the result is going to be NCM. Now what we are going to do is simply rewrite this contour integral in the form which is amenable to the steepest descent method or the saddle point method. So what we do is take a look at the integrand, which is 1 plus z raised to the power n by z to the power pn, that's an extra 1 by z, and we easily see that we can recast this in the form that we were looking for, f of z into e to the power some large parameter times g of z. Here the large parameter of course is a number capital N. So the small f of z is simply 1 by z in this example, and g of z is log of 1 plus z minus p times log of z. G prime z, the derivative is simply 1 by 1 plus z minus p by z, and setting that equal to 0 and solving for z to give you z0, the location of the saddle point, yields rather simply z0 equals p by 1 minus p. We can easily calculate the second derivative of g at z. We can easily calculate the second derivative of g at z, and hence at z0, and the value works out to be 1 minus p whole cube by p. Since g double prime z0 is positive, you have to ensure that g double prime z0 multiplied by z minus z0 whole square becomes negative. That is, z minus z0 whole square has to be negative, and so z minus z0 has to be purely imaginary, at least in the immediate vicinity of the saddle point. So our job is to deform our original contour, which is this green circle here, the unit circle traversed counterclockwise, into another contour which goes through this saddle point z0, which is at a real value, but it goes through z0 vertically, that is along the purely imaginary axis. And then when you are far away from the saddle point, you turn around and close the whole contour. Once you are far enough away from the saddle point, the exponential decrease has made your integrand small enough so that you don't have to worry about what you do far away. The contribution is going to come from the immediate vicinity of the saddle point anyway. The only other ingredient that you need for the calculation is the value of g of z0, which after a bit of algebra turns out to be something very simple. It's minus p times log of p minus 1 minus p into log of 1 minus p. And so our NCM calculation simply becomes 1 by 2 pi I, which is the residue formula factor outside, into the value of the integrand at z0, 1 by z0 e to the power n g z0, times the value for the Gaussian integral, which is root over 2 pi by n g double prime z0 times an extra factor which comes in because of the change of variables from z to tau. Note that at least in the immediate vicinity of the saddle point, you are going vertically up. So z is given by z0 plus tau e to the I phi, where e to the I phi, the space factor, has to be just I. So dz is I times d tau or e to the I pi by 2 times d tau. That's the extra e to the I pi by 2 factor that you get here. Of course, it's great that you have such a factor because NCM, being a binomial coefficient for integer arguments n and m, must ultimately be purely real. But you did have an I stuck in the formula here. This I gets exactly cancelled by this I, and so you are left with this expansion, which will be pretty familiar to you from statistical mechanics. That is, this binomial coefficient works out to be e to the minus n times p log p plus 1 minus p log 1 minus p divided by square root of 2 pi n into p by 1 minus p into 1 minus p. This requires a bit of algebra. Casting the final result in this particular form requires a bit of algebra, but it's pretty straightforward algebra and you should be able to carry it out yourself. The important point which I want to stress here is, in this particular case where you have a single saddle point, you still have to worry about only one major thing, which is in which direction must you cross the saddle point in order to achieve steepest descent. The situation will be a bit more complicated in cases where you have multiple saddle points, because there the problem of plenty that you have about the choice of a saddle point actually becomes quite acute. You will have to decide which saddle point to deform your contour through, or would you have to deform it through more than one? And again, in which direction would you cross each particular saddle point? Also, in this case, all this talk about hills and valleys becomes very, very important, because you have to ensure when you're crossing a saddle point, you do not stray into one of the hills surrounding that point. One example that we will deal with of a situation where there are multiple saddle points is the example of the asymptotic behavior of the ID functions. This, of course, is the immediate reason why we are dealing with this subject at all, and we are going to cover this in the next lecture. However, let me stress this. This particular method is actually much more useful than just an application to the asymptotics of the ID function. You would be using this in many different situations in mathematical physics, in statistical mechanics, in quantum mechanics, just because there are many occasions where you would want to figure out values of exponential integrals which are controlled by some large parameter. We will deal with the ID function asymptotics in the next lecture. Until then, bye.